Let's review systems of linear equations. A system of equations is a set of two or more equations with common variables. When we have equations of the form ax plus by equals c, we have x to the first and y to the first power. Those are linear equations, and the graphs of those equations will be straight lines. A solution to a system of equations is a set of values for the variables, in this case two variables, x and y, that make all of the equations true. There are three scenarios that can happen when we talk about a system of two linear equations and two variables. We can have one solution, in which case the lines intersect at a single point. Where will our solution be? Right here. It's going to be that one ordered pair that falls on both lines. No solutions means it's impossible to satisfy both equations at once. In other words, you cannot have a point that's on both lines. We call that an inconsistent system. And infinitely many solutions means that any point on the line is a solution. In other words, here's a solution, here's a solution, here's a solution. All of these are solutions, and of course all the ones in between as well, because these lie on both lines. It's important to remember that if you have a system like this in which your lines coincide, there are infinitely many solutions, but that does not mean every ordered pair of real numbers is a solution. What if I put an ordered pair here? Is this on the lines? No, it's not on either line. So this one is not a solution. So just remember that just because there are infinitely many solutions, that does not mean everything is a solution. We call this a dependent system. It's also called a consistent system because it means consistent basically means it is possible for your two lines to be satisfied simultaneously, which is true here and is also true in the first scenario. Inconsistent means it's impossible for both equations to be satisfied by the same point. We call this third situation dependent because one equation can be obtained from the other one, perhaps just by multiplying both sides by some number, rearranging it some way. If we were to write both lines in slope-intercept form, they would look identical. How do we solve linear equations systems? You should have seen before substitution and elimination, which is sometimes called the addition method. You can graph them and look at it graphically to figure out what point satisfies them both. For lines, since it's so easy to get exact answers some other way, there's really not any point in graphing. But when we have nonlinear equations and we cannot solve when we have nonlinear equations, sometimes it's impossible to solve explicitly for the solution using algebra, and in that case, using graphing to get an estimate of a solution is an excellent method. And we are also going to talk about matrices. So first we're going to review substitution and elimination, then we're going to move on to matrices. Let's start with an example. Let's suppose that we have a movie theater selling regular student tickets. The cost of two regular tickets and one student ticket is $16, and we're also given that the cost of three of each is $30. And we want to set up a system that will tell us what the price is of each type of ticket. Well, if you're going to set up a system, the first thing you want to do is determine what your variables are going to represent. And it's good to look and see what the question is asking, and in very many cases the quantities that the question is asking you for are good things to let your variables represent. So let's let x be the price of one regular ticket, and let's let y be the price of one student ticket. Okay, now let's set up our system. So in the first scenario, Cost of 2 regular tickets and 1 student ticket is $16. So how much do we pay for regular tickets? Well, we take the price of a regular ticket, multiply it by 2, and then we add on the price of 1 student ticket, and our total is $16. To do the second situation, the cost of 3 regular tickets, so we take the price of 1 regular ticket, multiply by 3. We take the price of 1 student ticket, multiply by 3. We add them together and we get $30. Here is our system. Now let's solve it. And just for a review, we're going to go ahead and solve it both ways. We're going to solve it by substitution and elimination. You should have seen this in an earlier algebra class. To solve a system by substitution, we're going to first solve one of the equations for one of the variables. So if I start with this, here's my system. Okay, so let's solve the first equation for y. So 2x plus y equals 16. Let's subtract 2x from both sides, and now we get this. And now what we're going to do is we are going to put that into the other equation in place of the y. And so that gives me 3x plus 3 times 16 minus 2x equals 30. Combining like terms gives me minus 3x equals 3 minus 4, 8 is negative 18. And therefore x is 6. And so then what you want to do is you want to take that x equals 6 and put it into either of your equations. So if I put it into here, and so my y is equal to 16 minus 12, which is 4. You could also, if you're alert, it's actually quicker to put it into here. Saves you a step. Anyway, so we have x equals 6, y equals 4. Make sure you answer the question posed by the original problem. So we want to know what the price is. So my regular tickets, remember that was x. So my regular tickets cost $6 and student tickets cost $4, which was y. Don't forget to check your answer. So 2x plus y equals 16. So let's put that in. So 2 times 6 plus 4 equals 16. Yep, that's true. And if we do the other one, so 3 times 6 plus 3 times 4, 18 plus 12 does indeed equal 30. You always want to check your answer. Okay. Okay, let's review how to solve a system by elimination. I'm just going to go ahead and do the same system. If we have 2x plus y equals 16, 3x plus 3y equals 30. What I want to do is I want to multiply one or both of my equations by a strategic number, both sides, so that when I add the equations, one or the other of the variables will be eliminated. So if I multiply this first equation by minus 3, you'll see why I'm doing that in a moment. If we multiply both sides by minus 3, that's going to give me minus 6x minus 3y equals minus 48. Here, let's leave the second equation alone. 3x plus 3y equals 30. Add the equations. So I get a negative 3x, 0y, which is the reason I multiplied that first equation by 3, and a negative 18. and so my x is 6. Now, you can either put the 6 back into one of the other equations, or you can do elimination again. Let's do elimination on the other variable. So, sometimes this is easier, particularly when you have a bunch of fractions. It can be real quick if you just do elimination on the other variable. This time, let's eliminate x. So let's multiply the first equation by 3 and the second equation by -2. That's going to give me 6x plus 3y equals 48. Down below, we're going to get a -6x, -6y, -60. And then when we add our equations, this time the x's are eliminated, and I get -3y equals -12, and so y is 4. And so we get the same answer that we got before. And make sure you remember to answer the question posed by the original problem. Okay, and in that previous example, we had a consistent independent system where we found one ordered pair that was a solution. There are some other things that can happen. If there's no solution, we'll get a contradiction. Let's look at this example. Let's solve this equation, this system, by elimination. If I multiply this first one by, actually let's multiply this one by -3 to eliminate the y's. And so this is going to give me -9y. Actually, before we do anything, let's rewrite this equation so that our variables in the same order and we don't get mixed up like I almost did. Here we've got -2x plus 3y equals 15, and then here we've got 4x minus 6y equals -6. Now we're going to do elimination. Let's multiply our first equation by 2. And so that's going to give me a -4x positive 6y equals 30. Second equation remains unchanged. And now when we add them, we get 0x plus 0y equals 24. So 0 equals 24. This is a false statement. If you get a statement like this, if this one's false, it came from very legitimate things by multiplying both sides of my first equation by 2. If we add two equations, since they are both, if I add this second equation to the first, these two sides ought to be equal since they are separated by an equal sign, so therefore I'm adding the same thing to both sides of that first equation. But yet when I did it, I got a contradiction. So if you get a false statement down here, that means it wasn't really possible for these two equations to both be true simultaneously. So that means that we have no solution, and our system is inconsistent. Okay, and why does this happen? This is because if we were to go graph those lines, we'll discover that they are parallel. They're going to have the same slope, but they're going to have different y-intercepts. Now let's look at the other special case that can happen. The consistent dependent system. Okay, let's solve this one by elimination as well. That should be an equal sign, and that also. Let's multiply our first equation by -3 and our second equation by 2. That's going to give me a -6x, -12y equals -18. 6x plus 12y equals 18. Now when we add these, we get 0 equals 0, which is a true statement. If you get this, this means that your system is dependent, which means there are infinitely many solutions, and that my lines coincide. Now, if I just state that there are infinitely many solutions, do you think that would be an acceptable answer to our goal, which was to solve the system? Well, think of it this way. If I gave you a linear equation and asked you to solve it, and you said, there's one solution, would that be a satisfactory answer? Or if there's a quadratic, and you were asked to solve it, and you said there are two solutions, would that be a satisfactory answer? No, stating the number of solutions is not the same as solving it. We need to find the solutions, and since there are infinitely many, we're not going to be able to write down each one individually. That would not be possible. But we can describe the solutions in a clear way. So here's what we're going to do. We're going to solve one of the equations for one of the variables. And when we have a system of two linear equations like this, it's very common to solve for y, because that will put our equation in slope-intercept form and it'll be obvious what the graph is. You could actually do either. When we get to matrices, we'll often find that it's easier to solve for a different variable in the two-variable case x. Let's go ahead and solve for one of them for y. And so here I should get 4y, if I look at the first one, equals negative 2x plus 6. If we divide both sides by 4, and my y is equal to negative 1/2 x plus 3 halves. And since these are the same line, you should get exactly the same thing if you chose to solve the second equation for y. So here's our answer. We're going to write it in set notation. It's going to be the set of all ordered pairs, x, y, such that x is any real number, and that y is equal to negative 1/2 x plus 3 halves. And that way it's very clear what the answer is. If you have an ordered pair, you can check this to see if it qualifies to be a solution. If you wanted to create solutions, you could just start picking values for x and using this to solve for y. So don't just write infinitely many solutions. You need to say what they are.